A website goes dark for half a second. The container that served it is gone. Kubernetes spins up a replacement on another machine and the page loads again. But the uploaded photos are missing. The shopping cart is empty. The database looks brand new. That is the quiet crisis at the heart of container platforms. Pods are designed to die. They crash, they get rescheduled, they get replaced during a rollout. Speed and disposability are the point. Data is not disposable. A customer order, a user profile, a product catalog, those have to outlive the process that last wrote them. So here's the question this story is really about. If the application survives by restarting somewhere else, where does its memory live? Kubernetes does not solve that with a single magic disk. It solves it with a layered negotiation between what an app asks for, what the cluster owns, and what actually sits on metal or cloud storage. The first answer people reach for is simple, and it is not enough. Meet the first compromise, the volume. Think of a volume as a shared folder that Kubernetes attaches to a pod. Every container inside that pod can see the same files. If one container crashes and restarts, the files are still there. For a web server and a helper sidecar that both need the same config, that is huge. But notice the catch. The volume's life is tied to the pod's life. When the pod is deleted, not just restarted, but actually destroyed, ordinary volume data usually goes with it. Empty dir is the clearest example. It is perfect for scratch space shared inside one pod, and it vanishes when that pod is gone. So volumes answer one half of the problem. They decouple data from a single container process. They do not decouple data from the pod itself. And in a real cluster, pods get replaced all the time. The storage has to escape the pod. That is where a different kind of object enters the story, one that lives at cluster scope, not inside any single application. Enter the persistent volume, the PV. Personify it as a reserved warehouse shelf. Pods are temporary workers who come and go. The shelf stays, whether or not anyone is standing in front of it today. A persistent volume is cluster-level storage. Its life cycle is independent of any pod. Under the hood, it might be an NFS share, an ISCSI target, a cloud disk, or a path on a node. The PV hides those details behind one Kubernetes object. Administrators can create PVs by hand, or the cluster can create them on demand later. Plugins matter here. NFS is the classic way to share files across many nodes. CSI, the Container Storage Interface, is the modern standard that lets vendors plug in their own drivers without rewriting Kubernetes itself. Flexibility and interoperability without forcing every developer to speak the dialect of every storage backend. Here is the part that matters. Developers should not have to know whether the shelf is metal, network, or cloud. They should only have to ask for what they need. Asking is a separate job, and it has its own object. That object is the persistent volume claim, the PVC. If the PV is the warehouse shelf, the PVC is the work order. The application does not grab a disk. It files a request, how much space and under what access rules. Those access modes are the contract language. Read write once, RWO, means one node can mount the volume read-write. Read-only many, ROX, means many nodes can mount it, but only for reading. Read-write many, RWX, means many nodes can read and write together. Pick the wrong mode and either your app cannot scale or your storage backend simply refuses the mount. A PVC can also name a storage class. That is how dynamic provisioning works. If no existing PV fits and a storage class is enabled, the cluster can create a new PV automatically on NFS, AWS EBS, GCP persistent disk, or whatever the class points at. The developer still never touches the backend. When a pod finally uses the PVC, it connects to the bound PV. Data stays safe even if that pod restarts or gets rescheduled. The request and the resource have to meet in the middle first. That meeting is the control plane's job. Watch the negotiation unfold. First, a cluster administrator defines persistent volumes, or configures storage classes so new volumes can appear on demand. Second, a developer or an application manifest creates a persistent volume claim with size, access mode, and maybe a class name. Third, the Kubernetes control plane matches the claim to a suitable volume and binds them together. If dynamic provisioning is on, a brand new PV may appear in that same moment. Only after the bind does a pod mount the claim, the way it would mount any other volume. From the application's point of view, it is just a path on disk. From the platform's point of view, three life cycles have been separated: the container, the pod, and the data. Picture the layers stacked: application on top, then the claim, then the volume, then physical storage, SAN, NAS, bare metal, or block storage in the cloud, under a storage controller. Multiple pods can each hold their own claim, each bound to its own volume, all funneled through that controller layer. Persistence is now a workflow, not a hope. But the story is not finished when the mount succeeds. Someone still has to decide what happens when the claim goes away. Let's make the abstract concrete with the sources manual example. No storage class magic, just a hand-built volume so the workflow is visible. An administrator writes a persistent volume manifest. Kind, persistent volume. Name, my PV. Capacity, 2 gigabytes. Access mode, read-write once. Reclaim policy, retain. Backend, a host path at /mnt/data. Apply it with kubectl apply. Then inspect with kubectl get PV and kubectl describe. The volume sits available, waiting for a claim. Next comes the claim, my PVC, requesting storage that can bind to that volume. Create it, then kubectl get PVC and describe the claim. When the control plane is happy, both sides show bound. The shelf has a work order stapled to it. Finally, a pod, an NGX container, mounts the claim at the path where NGX serves files. The pod does not mention host paths or cloud disks. It only names the claim. Check the pod, describe it, and the volume mount appears in the status. If that pod dies and a twin appears later with the same claim, the files are still there. One careful note: tutorial YAMLs sometimes drift in names and sizes across screenshots. Trust the workflow. Create volume, create claim, bind, mount more than any single file name. The pattern is the lesson. Persistence solves forgetting. It creates a new problem: stewardship. That reclaim policy on the example volume was retain. Retain means when the claim is deleted, the underlying storage and its data are kept. Safe for a database you cannot afford to lose by accident. Also a way to leave paid disks sitting around forever if nobody cleans them up. Other policies can recycle or delete more aggressively. Each choice is a trade-off between safety and cost. Best practice from the field notes is blunt. Prefer storage classes in cloud environments so provisioning stays consistent. Choose reclaim policies on purpose, not by default. Monitor unused and unbound volumes and claims. They are silent budget leaks. Right size requests so you do not reserve 10 gigabytes for a 200 megabyte config. And label everything with meaning so the next human can tell a staging cache from production customer data. Empty DWAR still has a place. Shared scratch space inside one pod is fine. Just never confuse it with a home for data that must survive the pod. The quiz in the source drives that home. Empty DWAR is shared within the pod and does not persist beyond it. The system that refused to forget can now hoard. Someone has to govern the shelves. Go back to the dark website. The pod is gone. A new one starts on a different node. This time it carries a claim, and that claim is already bound to a persistent volume whose files never left the cluster's storage layer. The photos load, the cart returns, the database opens where it left off. That is the resolution the platform was built for. Application life and data life are no longer the same clock. Containers restart, pods reschedule, the PVC is the ticket the new pod presents. The PV is the shelf that kept the goods. Physical storage, whatever plugin sits underneath, is the warehouse itself. NFS and CSI, manual volumes and storage classes, read-write once and read-write many, they are all machinery in service of one idea: disposable compute, durable state, negotiated through objects that refuse to let developers hardcode disks, and refuse to let administrators ignore what applications actually need. The opening stakes are answered. Memory has a home outside the process. And yet the field is not finished. As clusters grow, storage classes multiply, and reclaim policies collide with cost alerts and compliance rules, a harder question remains. How should platforms balance automatic persistence, retention, cost, and safe deletion when the same mechanism that saves a database can also strand 1,000 forgotten disks? That tension is not a footnote. It is the next chapter of the same story, keeping what matters without being owned by everything you once refused to lose.